Okay, last bit of the 2015 exam paper, and always the easiest bit, electricity. Okay, so a hollow conducting spherical shell of charge plus Q has a point charge minus Q placed at its centre. Which one of the following diagrams best illustrates the electric field lines? It's E. Why is it E? You have minus Q in the middle and plus Q in the shell. So if I draw any Gaussian surface outside there, the total charge inside is 0. So there is no flux lines crossing this shell, so there is no electric field. Every single one of these other ones has got some electric field outside the thing, but there's 0 charge, so can't be any. Okay, easy as pie. A hollow conducting spherical shell of charge plus Q has inner radius A and outer radius B. A point charge minus Q is placed at the centre of the shell. Yeah, it's the same as the previous one. Which one of the following diagrams best represents the variation of the electric potential V as a function of distance r from the point charge? Now I think the thing you need to remember is that the electric field is given by, I'm not sure it's plus or minus, it really doesn't matter, but it's dV dr. Okay, if we're looking at the radial electric field, okay, it's the electric field. So what's the story with the electric field? Well, if we look at this one here, it has an electric field pointing towards the middle, which gets stronger as you get towards the middle, and then there's no electric field in the conductor, and then outside there's also no electric field. So looking at this, which one has this attribute? No electric field outside, no electric field in the conductor. That looks really good. This one has got electric field inside the conductor. No. This one has no electric field inside the conductor, but it has electric field outside the conductor. No. This one has no electric field inside the conductor, but it has electric field outside the conductor. And plus it has an infinite electric field there. Doesn't make sense. This one's got 2 bits of infinite electric field, and so it can only be A. So easy. Right, consider 2 long coaxial cylinders with radius A and 2A respectively. The cylinders are uniformly charged. The inner cylinder has a linear charge density of 1 coulomb per meter. The outer cylinder has linear charge density lambda of minus 2 coulombs per meter. The radial electric field for R between A and 2A is. Now, what's the key here? The key here is that Gauss's law says if we're looking at the electric field in this zone here, we care not what the charge is on the outside. Okay? It's only the enclosed charge that matters. So the enclosed charge in an area 1 meter long of radius r is this lambda. So the number of field lines is lambda over epsilon naught, and the area is pi times r, because that's around there, times 1, so pi r, and yep. Okay. Oh, 2 pi r. 2 pi r is the distance around, so the area is 2 pi r times 1 lambda over epsilon naught. Why am I getting this wrong? Start again, John. The total flux is lambda over epsilon naught in 1 meter, because that's how much charge is in 1 meter. This needs to be divided by the area. Okay, so that if we want to find the electric field strength, we've got to take the amount of flux divided by the area. So the flux is all coming out at right angles to the surface there, and it's 1 over 2 pi r times 1 being the length. That's that one. Okay, easy peasy. And here is a classic. It's a classic because it can be asked in several different ways, as all good questions can. This one, we've got parallel plate capacitor. It's connected to a battery, charged and then disconnected. So then the plates of the capacitor are pulled apart to twice their separation. The ratio of the final energy stored in the capacitor to the initial is... Right, so I'm going to go with some formulas. Capacitance. C equals Q over V. Okay, and energy, the energy stored in a capacitor is a half C V squared. And also the capacitance is epsilon naught A over D. For a parallel C, the capacitance is epsilon naught A over D. Right, where D is the separation. Good. Now I've got everything I need. So initially, the initial energy is simply a half CV squared. Now, we pull the plates apart to twice their separation. So in other words, now instead of we double that, so now we've got a capacitance of a half C. Alright, that's our final capacitance, a half C. But note that our charge must stay the same. Why? Because the battery's been disconnected, there's nowhere else for the charge to go, it's stuck on those plates. So now we've got a half C is Q over our new V. Our new V, we'll call it VF. So therefore VF must be equal to twice the initial voltage. Okay? So now we're ready to work out our final energy. Our final energy is equal to a half times our new capacitance, which is a half C, times our new voltage, which is 2V squared. And so that's a half times 2 squared is, so it basically becomes the CV squared. In other words, it's twice what it was before. So it's B. It's twice the energy. Okay. Now, you might say, well, why is it twice the energy? Well, think about it. You've got the two plates of the capacitor sitting there. They're attracting each other because they're holding opposite charges. The battery's been removed so those charges can't go anywhere. And you pull them apart. What do you do when you pull them apart? You do work. That work is stored in the capacitor. So by doing that work, you have increased the energy of the capacitor. So the only potential answers were A or B, and it turned out that if you do the maths, it's B. Done.